Hello and welcome to the course of Software Defined Networking. In today's lecture, we will learn about an important topic and that is known as OpenFlow. I'm sure you have the basic idea of OpenFlow because we have talked about the OpenFlow at several occasions in this course. The contents for this presentation, first we are going to learn about the basic concept of OpenFlow, an overview, a historical aspect of the OpenFlow. After that, we will see different components of the OpenFlow like OpenFlow Switch, controller protocol, and a secure channel. After that, we will explore in details the first official version, you can say, of the OpenFlow, that is 1.0. However, there are other versions available as well, like 1.1, 2, 3, 4, 5, and so on. So we will not go into the details of each and every version that is mentioned here, but we will highlight the changes when we move from one version to the next version. So what are being added there? We will just see an overview of the changes. Let's start with an overview. This is the SDN architecture, and we are pretty much familiar with this architecture. Here is a component which is known as OpenFlow, and this is actually at the southbound API, or you can say it link the two layers, the data plane layer with the control layer. I have a very basic question, and I would like that you think on this question. By the way, this is very simple to answer, and I'm sure you would be able to answer at least at the end of this lecture. And the question is whether the SDN and OpenFlow are one and the same thing or they are not the same thing. So you have to think on this question. Well, OpenFlow, it actually defines both the communication protocol between the SDN data plane and the SDN control plane. And beside from this communication protocol, it is actually part of the behavior of the data plane, the things that actually happened inside the data plane layer. So actually, southbound API has other options available as well beside from OpenFlow. But there is going to be like the industrial standard for the SDN. So that is why we are going to explore this OpenFlow. So actually it defines the communication protocol between the two planes as well as the behavior of this data plane. However, it is important to remember that it does not describe the behavior of this controller, the SDN controller itself. While there are other approaches to SDN, as I just mentioned, OpenFlow is the only non-proprietary general purpose protocol for programming the forwarding plane of the SDN switches. As I just mentioned, it actually take parts in defining the behavior of the data plane. So at the data plane layer, we have the switches that are known as the SDN switches, and the switches has the forwarding planes. So it is actually the protocol for programming the forwarding plane of these SDN switches. Now, OpenFlow system actually consists of different components. For example, the first component is the OpenFlow controller that will communicate to one or more OpenFlow switches. The OpenFlow protocol is another component which actually define the messages, their formats, their types that are going to be exchanged between the controller at the control plane and the devices, the switches at the data plane. The OpenFlow behavior will specify how the devices should react in various situations. and how they should respond to the commands that they receive from the SDN controller. And we know that there is a communication between the controller and the devices because SDN controller is our boss. He's actually managing the forwarding rules of these devices. So there must be communication between these two worlds. And that communication is possible with the help of OpenFlow protocol. Okay, some more points about the OpenFlow. Let me tell you about the historical background of this OpenFlow. Uh, there is a non-profit organization. Let me show you. Okay, so I look at the slide. There was a non-profit internet organization known as OpenFlow.org, and it was established in 2008. Their purpose was to promote and support OpenFlow. In the early years, the physical organization was really just just a few people involved in the group at the Stanford University. And then they released the first version of the OpenFlow. That version was referred as 1.00. And this version actually appeared in December 2009. Although before this version, there were pre-releases existed, but they were used mostly for experimental purposes. So the actual version developed by the OpenFlow and make available to the public, that was 1.00. Now, after this version, the development and management of the specification was transferred to the ONF in March 2011. Actually, this ONF was created for the purpose to accelerate the delivery and also the commercialization of SDN. So a number of SDN proponents that offer SDN solutions that are not actually based on OpenFlow. What I mean to say that there are other solutions available beside from OpenFlow, but the ONF recommended the use of OpenFlow, and they take the responsibility in order to accelerate the delivery and commercialization of SDN. For the ONF, OpenFlow is and it will remain at the core of the SDN vision for the future. For this reason, ONF has become the responsible entity for the evolving OpenFlow specification. So OpenFlow, historical perspective, in summary, it was started in 2008 and it was a non-profit organization, and that was the OpenFlow.org. It contains only a few members from the Stanford University, and they released the first version publicly available, that was 1.00 in December 2009. And then the responsibility was transferred to the ONF in March 2011. So to accelerate the delivery and commercialization of the SDN. Other solutions are also available for the SDN, for the southbound API, but the ONF selected this at the core of the SDN to meet the future vision. Okay, so OpenFlow is actually an attempt to allow the programming of the different implementation of the switches that conform to this new paradigm proposed by the ONF. So this was a brief overview of the OpenFlow. Now we are going to study the components of the OpenFlow one by one. In this regard, the very first component of the OpenFlow is the OpenFlow Switch. In this picture, the basic function of an OpenFlow switch and its relation to a controller is depicted. We have a switch and we have a controller, and they both communicate with one another by using an OpenFlow protocol. So this component will be described later, the protocol will be described later, the secure channel will be described later, but now we are going to focus here on the switch. And this is actually the core function of this switch is to take packets, and the packets actually arrived at one of the port that are mentioned here, like port 1, 2, 3, 4 and so on. Switch has different ports. Packet arrived on those ports. In this particular case, you can see path X that is on port number 2. Once this switch receive a packet on any of the port, it will forward it through another port, in this case port N. So the basic responsibility is forwarding of packets. It receive a packet on one port X and it forward the packet on another port, for example port number N. However, before forwarding the packet, it is possible, and in some cases it is necessary, to do some modification to the packets along the journey, along the way. A unique aspect of OpenFlow Switch is embodied in the packet matching function as shown here. We have a packet matching function, and we do have a table that is known as the flow table, and you are familiar with the flow table. So we have a flow table, we have a matching function, and you can see that we have drawn different lines here. Some are like the arrowed, single arrowed and double arrowed lines are shown here. So the wide gray double arrow line here, it starts in decision, logic. It shows a match with a particular entry in the table and directs the new matched packet to an action box here on the right side. This action box has 3 fundamental options to deal with the arrived packet. Like you arrive a packet at port, before forwarding that packet, we need to take certain modifications to the packet if required. So the packet is handed over to the matching function, and then the flow table, and based on this, the entries of this flow table, certain actions are taken on the packet. Basically 3 actions need to be taken. Action number A, as you can see, forward the packet out a local port, possibly modifying certain headers, but in most of the cases just forward the packet. That is the simple case. Case number B, drop the packet. If the packet doesn't meet any criteria in the table, then we can drop the packet. Although we can send it to the controller, but we will see that in case number C. So case number B, simply drop the packet, while case number C, pass the packet to the controller. In this case number C, the packet is passed to the controller over a secure channel as shown here. If the controller has either a control message or a data packet to give to the switch, the controller also uses this same secure channel in the reverse direction. When the controller has a packet to forward out through the switch, it uses the OpenFlow message, and that particular message used by the controller is known as packet out. On the other side, if the switch want to communicate, it will use a packet, and that packet is known as packet in message. So we can see in this figure that such a data packet which is coming from the controller may take two different paths. Okay, so we have like a packet coming from the controller. It can take two different paths. You see, I highlighted them. The first path is logic, OpenFlow logic. Both are denoted by Y, but the first one is the logic part. In the rightmost case, the controller directly specify the output port, and the packet is passed to that port N in this example. Like there are two cases. The first case is just to directly route the packet to an output port, or just to send the packet to the matching function, the logical part here. So in the leftmost path Y case here, the controller indicates that it wishes to defer the forwarding decision to the packet matching logic. A given OpenFlow switch implementation is easier. If you have this switch and if you want to implement this logic, that is simple. There are two possibilities available. The first one is OpenFlow only. The second one is OpenFlow hybrid approach. An OpenFlow only switch is one that will forward packets only according to the OpenFlow logic described here. While the hybrid approach is a switch that can also switch packets in its legacy mode. For example, the Ethernet switches or IP router, they can also handle those packets. One can view the hybrid case as an OpenFlow switch that will actually reside next to a completely independent traditional switch. However, such hybrid switch will require pre-processing classification mechanisms that directs the packet to either the OpenFlow processing or the traditional processing. So this was the basic functionality of the OpenFlow switch. Let me summarize. There are different ports in the switch. Packet will arrive on any of this port. Then the packet is forwarded to the matching function logic. And then the logic is like connected with the flow table, and certain actions are performed based on the matching with any entry in the table. Three actions are possibly performed: forward the packet on the output port, drop the packet, or forward the packet by using a secure channel to the controller. And then the controller has two options. Either it will instruct the packet to be forwarded on a port like port N here, or it may request the matching function to take another action. Our next component of the OpenFlow is the controller, OpenFlow controller. Modern internet switches, they actually make thousands and even millions of decisions per second. And what are those decisions? They are simple decisions, whether to forward an incoming packet or to drop an incoming packet. If we need to forward, what set of output port it should be forwarded, and what header fields in the packet may need to be modified, added, or removed. Now the things are becoming complex for these switches, because it's not just forwarding. It's like taking some intelligent decisions. studying the packet headers, the packet fields. So the OpenFlow control plane, actually its responsibilities are different from the traditional switches or traditional control plane, the legacy control plane. It is differ in three ways. First, we know that it can program different data plane elements with a common standard language. That is what we have studied in SDN. And that is what is known as the OpenFlow, which is like we want to program the data plane elements, the switches, the hardware with a common standard language. Second difference between an OpenFlow controller and a traditional switch controller is that the OpenFlow controller, it exists on a separate hardware devices than that of the forwarding plane. Like we separate the two worlds, the data plane and the forwarding and the controller plane. So actually it exists on a separate hardware device than that of the forwarding plane. Unlike traditional switches where the control plane and the data plane are on the same physical device. This separation is made possible because the controller can program the data plane elements remotely over the internet. And the third difference is that the controller can program multiple data plane elements from a single control plane instance. The OpenFlow controller is now responsible for programming all the packets. It is actually responsible for the matching logic. It is also responsible for forwarding rules, definition of the forwarding rules in the switch. The rules are followed by the switch, but they are defined by the controller. In case of a traditional router, the router would run routing algorithms to determine how to program its forwarding table. Then that function or an equivalent replacement to it is now performed by the controller. The logic is the same. We need forwarding rules. We need forwarding tables. But now we are programming them and we are controlling them from the controller. And here we can see at the bottom we have the switches which have the logic that we just saw, the flow tables and the actions performed by the switch, and we have a secure communication channel. The OpenFlow controller will define the formats of the messages that we will see in a moment. And then we have bi-directional communication between the switch and the controller, and that is over a secure medium. So we have like an inquiry and then a response from the controller. What to do with the packet? Straightforward, forward it on an output port as we just saw previously, or send it back to the logical part and make another decision. So that is actually the controller. So in summary, in the traditional switches, the routing functionalities, the control and the data plane, they are combined in a one physical box. But in the SDN, we actually separate them. And there are three differences that we just mentioned. And the controller is actually responsible for programming all of the packet matching and forwarding rules in the switch. The next component of the OpenFlow is the OpenFlow Protocol. This is the part that we are going to study now. OpenFlow Protocol. Actually, the OpenFlow Protocol, you are familiar with the word protocol, the syntax and format and semantic stuff, the language of communication. So in this regard, the OpenFlow Protocol actually describe the messages that exchanges that take place between the OpenFlow controller and the OpenFlow switch. And typically this protocol is implemented on top of TLS. And in the previous lecture, we talked about the TLS. It's actually providing a secure OpenFlow channel. So that is the basic concept of the OpenFlow protocol. It defines the communication, the messages that exchange between the controller and the switch over a secure medium. OpenFlow protocol actually defines the communication. This protocol, OpenFlow protocol, is what most uniquely identifies the OpenFlow technology. As it is essence, the protocol will consist of a set of messages, and those messages are sent from the controller to the switch, and corresponding set of messages that are sent in the opposite direction. The message collectively allow the controller to program this switch so as to allow fine-grained control over the switching of the traffic, the user traffic, how to route traffic from an input source to an output, from an input port to an output port. The most basic programming defines, modifies, and delete these flows. What is flow? We know is a set of packets that are transferred from one network endpoint to another endpoint. Now these endpoints, as we know, it may be like IP. They may be defined as the IP addresses, port number, TCP port, TCP or UDP port, or maybe virtual LAN endpoints. So it could be anything. Okay, now the rules. One set of rules that describe the forwarding action that the devices should take or on the packets that actually belong to the same flow. When the controller defines a flow, it is providing the switch with the information it needs to know how to treat the incoming packet that will match that flow. For example, we have a flow that is dedicated for a specific end device that is in a VLAN, connected to a VLAN. So if a new packet is arrived for that, the device must know what to do with that specific packet because it belongs to a flow. The most basic prescription for treatment of an incoming packet, as we just saw, they are denoted by the A, B, and C. These three options are to forward the packet out to one or more output ports, to drop the packet, or pass the packet, as in case of C, to the controller for exception handling, or maybe for further guidance from the controller. Now, the OpenFlow protocol is evolved significantly with each version of the OpenFlow. We know there are different versions. So in every version, the role of the OpenFlow, the duties, the responsibilities, they are modified. Now, with the early releases of the OpenFlow protocol, of the OpenFlow version, there were problems, and those problems are now addressed in the other versions, the latest version. Now the OpenFlow is like viewed as the more sophisticated part of the OpenFlow. Okay, now the fourth component of the OpenFlow is the secure channel, and the channel is between the controller and the OpenFlow switch. The secure channel is actually the path, and this path is used for communication between the OpenFlow controller and the OpenFlow device. Generally, this communication is secure, as I just mentioned. It is secured by using TLS based asymmetric encryption. This connection may be in band or out of band. These are the two variants of the secure channel. In the out of band example, it is like The secure channel connection, you can see here, it will enters in the switch by using a, a dedicated port, and that port is represented by Z here. Okay, let me rewind. If we have an out of band connection, then the secure channel connection enters by using a dedicated port, that is port Z. Actually, this is not switched by the OpenFlow data plane. Some legacy network stack will deliver the OpenFlow messages via the secure channel to the data plane, where all the OpenFlow messages are passed and handled. So the out of band secure channel is only relevant in case if we are using the OpenFlow hybrid switch. While normally we will be using, or the SDN will use, the in-band. In this example, you can see the OpenFlow messages from the controller arriving by using a port, and that port is K. And this port is actually part of the OpenFlow data plane. So now we know the main difference between port Z and port K. This port K is actually part of the switch, while port Z is not part. This is the case if we are using the hybrid switch, while this is the case if we are using the OpenFlow switch. Okay, so port K is actually part. In this case, these packets will be handled by the OpenFlow packet matching logic as shown here. However, in this case, we are not passing it to the matching function. Note that when the controller and all the switches that it control are located entirely within a tightly controlled environment like a data center, it may be wise to consider not using the TLS based encryption to secure this channel. This is because there is a performance overhead incurred by using this type of security, the TLS security. And if it is not necessary like in the data center environment, it is preferable to not pay this performance penalty. Another argument against using the TLS based encryption is that it may be used incorrectly. Why? Because to put TLS in practice, one must obtain and configure security certificates for each devices, which can be time consuming and also error prone. Misconfiguration can lead to other vulnerabilities. So if you are not familiar with such stuff, it is also recommended not to use the TLS option. Now we have studied the 4 different components of an OpenFlow. Now let's see the first version of OpenFlow. And the first version was, the official version was 1.0, and it was released in December 2009. This is like the initial release of the OpenFlow. Indeed, year of works and multiple point releases precede the OpenFlow 1.0, but we will only focusing on this first version. Okay, so here are some of the concepts related with this version 1. The first concept is date of the port and port queue. If you give some attention, we have considered a scenario at the beginning of this lecture, and we are exploring things by using the same scenario. So in this way, you would be able to understand it in a better way. Again, we have the same OpenFlow environment. The different component, the switch is there, the secure channel is there, the communication protocol is there, and the controller is there. Now we are going to see what is inside these ports. Okay, like we have port 1, 2, 3 up to port N. So OpenFlow port Port here actually correspond to a physical port. Not always the case, but it corresponds to a physical port. And this concept is expanded in subsequent releases of the OpenFlow. For many years, sophisticated switches have supported multiple queues per physical port, and these queues are generally served by scheduling algorithms that allow the provisioning of different quality of service level for different types of packets. Now, OpenFlow embraces this concept and permit a flow to be mapped to an already defined queue at an output port. Now, you don't have queues only in the incoming port, you do have quality of service provisioning queues available at the outgoing ports as well. So if we look back at this picture, the output of a packet on port N has been zoomed here. Hence, if we zoom this portion, this port N here, we reveal what we now see here. We reveal that, hey, there on this output port, we can see action boxes. We can see different queues and the packet being processed to queue 1 here. Like if you see at a broader level, you will see that the packet has just been forwarded to port N. But inside that port, we have different queues, port queues, and the packet based on the quality of service, it has been assigned to first queue. Note that the support for quality of service is very basic in this version 1.0, and this support is actually expanded considerably in the latter versions. But for us, the important is that we have ports which correspond to physical ports, and we do have queues defined inside those ports for providing different quality of service uh, level for different types of packets. Now, let's move to the second concept, and that is the flow table. We already studied flow table. Yes, so the flow table lies actually at the core of the definition of an OpenFlow switch. And we also depict a very generic flow table here. So you can see a flow table consists of flow entries. In this case, we have like entry 0, 1 up to entry M. A flow entry now, it will consist of header fields, some counters, and some actions. And these actions are associated with that entry. The header fields are actually used as a matching criteria to determine if an incoming packet matches this entry. If a match exists, then the packet belongs to this flow. On the other side, the counters, as I mentioned in my previous lecture, they are used to track statistical properties related to the flow, such as how many packets have been forwarded, how many packets have been dropped, how many packets are sent to the controller, and things like that. While the actions, they actually prescribe what the switch should do with the packet after matching this entry. Okay. Now we will see the actions in the next slide that are related with the packet matching, how the packets are actually matched. So these are the three basic elements: the header fields, the counters, and the actions performed. Now let's see the packet matching criteria. How packets are matched with a flow. When a packet arrives at the OpenFlow switch from an input port, or maybe in some cases the packet is arrived from a controller. Now the packet that it received or the packet received by the OpenFlow switch is matched against the flow table to determine if there is any matching flow entry there in the table. The following match fields that you can see here, they are actually associated with the incoming packet, and these fields may be used for matching against the flow entries. And some of these are not all of the fields, but some of the fields that are used for matching purposes, and these are like switching input port VLAN ID, and we have the priority for the VLAN, IP addresses, frame type, destination source addresses, Ethernet source address, destination address, maybe port numbers, what is the IP protocol used, and things like that. So these are different criteria that we can use for matching a packet to a flow. Actually, 12 different rules are defined for packet matching in the OpenFlow, and these are referred to basic tuple of match field. The flow entries are processed in order. Okay, if you receive a packet, you have to compare it with the entries, and then the comparison is made in order. Once a match is found, no further match attempts are made against the flow table. There may be additional flow tables against which packet matching may continue, but we stop there once we found the first match. Because of this, it is possible for there to be, it is possible that we have multiple matching flows entries for a packet to be present in a flow table, but only the first flow entry to match is meaningful. The other will not be found as packet matching. So we stop upon the first match. The version that we are studying, the version 1.0 specification, is silent about which of these rules are required and which of these rules are actually optional. What I mean to say, we studied different fields. In these fields, which fields are required to be matched, which fields are optional for matching. So the specification doesn't tell us anything about this. The ONF has later on clarified this confusion by defining 3 types of conformance in their version 1.0. What are those 3 levels? The 3 levels are full conformance and layer 2 conformance and layer 3 conformance. Full conformance meaning all 12 matches field are supported. Layer 2 conformance, only the layer 2 header fields matching is supported. And the layer 3 conformance, only the layer 3 header fields matching is supported. So if the end of the flow table is reached, it is also possible we reach to the end without finding a match. Such situation is known as table miss. In this event of a table miss, the packet is forwarded to the controller, noting that this is no longer strictly true in the later versions. If a matching flow entry is not found in the later versions, the action associated with the flow entry determine how the packet is handled. And mostly the OpenFlow switch entries is forward this packet, maybe drop this packet. But in this version that we are studying, version 1.0, the packet is forwarded to the controller. Now this is the packet matching criteria. After matching a packet, we need to perform certain actions. Maybe we need to forward the packet, to drop the packet, and things like that. So the required actions that must be supported by a flow entry are to either forward the packet or drop the packet. The most common case is that the output actions specify a physical port on which the packet should be forwarded. There are, however, different virtual ports defined in this version 1.0 that have special significance for the output action that is performed. What are those virtual ports? They are local, all, controller, in, port, and table. And you can see them in bold and capital letters. Like we have the local, all is not mentioned here. Why? We will study it. Controller is there, in port is there, and the table is there. These are actually the actions related to forwarding. A packet may be forwarded to one of these. And these are like the 5 virtual ports. Not the actual ports are here, but these are like the virtual ports, just for our understanding. What does local mean? Local dictates that the packet should be forwarded to the switch local control software. We have OpenFlow Switch side controller. The actual controller is here, but inside the switch we have a local OpenFlow Switch controller. So the local means that the packet has to be forwarded to this local OpenFlow controller software. And this local is used when OpenFlow messages from the controller are received. You receive a message from the controller, not from the ports. Then the local is used. And these are the messages from the controller are received on a port that is receiving packets switched by the OpenFlow data plane. This local actually indicates that the packet need to be processed by the local OpenFlow control software. All as the name indicates, is used to flood a packet out on all ports on the switch, except from the input port on which it is received. This provides like the broadcast capability of the OpenFlow switch. If you want to flood a packet, if you want to send a packet, broadcast a packet on all the available output ports, except from the one on which it is arrived. So that is the all. And then we have the controller port, virtual port. Controller actually indicates that the switch should forward this packet to the controller, the actual controller, not the local one. On the other side, the input instruct this switch to forward the packet back out on the port on which it arrived. Input port. You receive a packet from port number 2, and then you are forwarding the packet back on the same port on which it was arrived. Effectively, in port normally creates a loop back situation, which could be used for certain scenarios, but could be avoided in certain scenarios as well. Okay, so that is the input. And finally, we have the table, virtual port, the table, which only applies to packets that the controller sends to the switch. Such packet arrived is part of the packet out message. Remember, when the controller send a message to the switch, then the message is the packet out message, and it arrived from the controller, and that for that we use the table. And it include actually an action list, and this action list will generally contain an output action, which will specify, for example, a port number on which the packet should be sent. The controller may wish to directly specify the output port for this data packet, or if it wishes the output port to be determined by the normal OpenFlow packet processing pipeline, it may do so by stipulating the table as the output port. And these two options are depicted or were depicted by the Y arrow as we just saw in the previous slides. Now, there are 2 additional virtual ports, and they are normal and flood. but support for these in the version 1.0 is optional. Okay, so the first one is normal virtual port. When the output action forwards a packet to the normal virtual port, it sends the packet to the legacy forwarding logic of the switch. That is the local one again. Well, the use of this normal only makes sense again in the case of a hybrid switch. Okay, the remaining virtual port is the flood. In this case, the switch will send a copy of the packet out all ports except against on the ingress port from which it was received. Okay, now you can see all the virtual ports here except from the all and except from the flood. And they are not depicted just because it will make the figure messy. It will make the figure full of arrows because you are going to forward the packet on all the possible ports. Okay, so the representation will be complex. Okay, so this was about the different types of ports, virtual ports that are used for forwarding the packet. Next component is related with the protocol, and they are the different type of messages that are defined. The messaging between the controller and the switch is transmitted over a secure channel. We know it. This secure channel is implemented via the TLS over TCP. We also know it. Now, if the switch knows the IP address of the controller, then the switch will initiate this connection. Each message between the controller and the switch start with the OpenFlow header. This header specifies the OpenFlow version number, the type of the message, the length of the message, the transaction ID of the message, and other information. So the various message type in version 1.0, they are listed here in this table. Actually, the messages fall in three general categories: symmetric, and we have the controller switch, and asynchronous. But these are only the most important types of messages in the normal context. We do have other type of messages that are not mentioned over here, but just to give you an overview that all the messages are being defined. Okay, and how actually the communication take place is also shown here. Let me highlight some of the messages that are mentioned here, like the hello message. And the hello messages are exchanged after the secure channel has been established to determine the highest OpenFlow version number supported by the peers. The echo messages here, request and reply, they are used by either side during the life of the channel to assertion that the connection is still alive and to measure the current latency or bandwidth. Similarly, we have the vendor message, and they are available for vendor specific experimentation or maybe enhancement. And the messages like the packet in and also the packet out. Where is packet out? Yes, the packet out. They are important and we studied about them. The packet in message is how the switch. Okay, this is a message generated by the switch. So this message is how the switch passes data packet back to the controller for exception handling. And the control plane traffic will usually be sent back to the controller with the help of this message. And we do have the message, the packet out, which is used by the controller to send data to the switch. And similarly, we have like the flow removed. We do have like the port status, which is used to communicate changes in port status, whether by direct user intervention or maybe by a physical change in the communication medium itself. So every message has a category, and the categories, as I just mentioned, they are symmetric, asynchronous, and controller switch. Okay, so if the communication is between like the controller and switch, so it is going to be like in the category of controller switch. But sometime a message may be like, for example, packet in and packet out. They are also for the communicate. They are also used between the communication between the switch and the controller, but it is like asymmetric. Okay, so every message belong to a specific category, and every message serve a purpose, and they are mostly used for communication between the controller and the switch, and they are used in a sequence. One of the example of the control switch protocol session is mentioned in this figure. You can explain this. You can give attention to this. If you're interested, you can see the sequence of the message by yourself. Okay, now this was about the first version 1.0. As I mentioned at the beginning of this lecture, we do have other versions available. Okay, so OpenFlow 1.1 was the next version in the series. And I just mentioned the modification that were made to this new version. What were those modifications? You can see here. The first modification was made to the multiple flow tables. It is like a more sophisticated approach now of packet forwarding in the OpenFlow. This is one of the brilliant feature. And then the concept of groups was introduced, MPLS and VLAN support, virtual ports, and controller connection failure. Then we have some modification. It was, by the way, released in 2011. Then we have the next version 1.2, and you can see the features added over here. Then we have the next version 1.3, and the features like the cookies now, the concept of cookies and things like that, IP version 6 support, on-demand support, and things like that. It was released in 2012. And then we have the 1.4 and 1.5 as well, and their features. Okay, now you have to search on the internet. What is the current available version of OpenFlow? Available to the public, available for experimentation, available for doing simulations or things like that. You have to search for it. That's it. Thank you so much. See you. Take care and goodbye.